Welcome to Pre-Calc Lesson 2.2, Polynomial Functions. We're looking today at the leading terms test for polynomial n behavior, something that you learned in Algebra 2. We're reviewing it here. And our other learning target is to know the number of possible zeros and turning points when we look at the polynomial equation. We did an exploration in class today on this, so most of you kind of drew your conclusions pretty early on. Pairing that with what you should remember from Algebra 2, you should be pretty solid on this, but we're going to take a quick look at this. Monomial functions are functions in the form p of x equals a times x to the n, where n is a positive integer whole number. So we're looking at monomial functions. Polynomial functions are formed by the sum and differences of polynomial functions. So you can't have a negative exponent or a fractional exponent when you're dealing with polynomial functions. The degree of the polynomial is the greatest exponent. The leading coefficient is the coefficient of the variable with the greatest exponent or greatest degree. So we're looking at the leading term test. We need to look at the exponent with the highest, we need to look at the highest exponent and look at its coefficient. So you did this in Algebra 2, and it's really hard to see this graph, I'm sorry about that, but you can see the function. This is an odd degreed function. You can see like a linear function. An odd function acts like a linear function. It just has turning points and x-intercepts in the middle. But the end behavior for an odd function is much like that for a line, which is also an odd degree x to the first. It will either go up as you go to the right and down as you go to the left, or down as you go to the right and up as you go to the left. So how we write that, or how we used to write that, is that as x approaches negative infinity, what that means is as we go to the left infinitely, f of x for this one decreases infinitely. And as x increases infinitely, that's why we see the positive infinity, f of x increases infinitely. That's for this first one. It's like the line with a positive slope, positive lead coefficient for odd. Whereas negative lead coefficient for odd, as x approaches negative infinity, or as x goes to the left infinitely and to the right infinitely, what happens to the height of the graph, or the output f of x? Well, when we have a negative lead coefficient on an odd degreed polynomial, the height, as you go to the left, the height goes up infinitely. As you go to the right, it goes down infinitely. Similarly, when we're looking with even degree, right, they either go up together, that's positive lead coefficient on even, or negative lead coefficient on even, they'll go down together. So for positive lead coefficient even, we have as x goes left infinitely and as x goes right infinitely. If it's positive, the height on both sides is just going to go up infinitely. And if it's negative, lead coefficient, as we go to the left and as we go to the right, the outputs, the height of the graph, will go down infinitely. And behavior describes what happens as you get to y as x gets incrementally smaller, incrementally large. So as it increasingly grows larger, or as increasingly grows smaller. Instead of as x approaches infinity, as x approaches positive infinity, we use what's called limit notation. So we're at this point, we're not really going to talk about limits till you get to calculus. We're talking about limit notation, and that's saying, this is just saying the same thing. This right here, limit, and it has this subscript underneath of x to the negative, x approaching negative infinity, or limit as x approaches positive infinity, you don't have to put the positive sign, of f of x equals of f of x equals, we're saying what's happening to this. Does it increase infinitely, so we'd put positive infinity, or does it decrease infinitely? So we're changing the notation. Instead of saying as x does this, f of x does this. Instead of writing out that long sentence, we're doing limit of f of x, we're doing the subscript, and this is saying as we go left. So we're saying what happens to the height as we go to the left. Limit of f of x as x approaches positive infinity. What happens to the height as we approach positive infinity? Oh, the height goes down infinitely, or oh, the height goes up infinitely. This is called limit notation. We will be using this for the rest of the course, so you need to be comfortable with limit notation. But this should primarily be reviewed using the leading terms test. Look at the highest degree. If it's even, you know the ends move together. If it's odd, they move opposite directions. And then you look at the lead coefficient. If it's positive, you think of a positive slope, or in the case of an even, an open parabola, because it's going to have lots of twists and turns in there, but the ends behave just like a parabola. If it's negative for odd, you think of a line with a negative slope. If it's negative for even, you think of a parabola that opens down. You don't care about the twists and turns in the middle. That's what we care about when we're looking for the x-intercepts and turning points. But the end behavior behaves much like a parabola or quadratic function. So let's take a look at some quick examples. Describe the end behavior of the graph using limits. So we're supposed to use limit notation. Explain your reasoning using the leading term test. This is in standard form, so the leading term is 3x to the fourth. It's an even degree, this is my explanation, and a positive lead coefficient. Because it's an even and positive lead coefficient, I'm treating that like a parabola that opens up. I don't care what happens in the middle, the two ends open up together. So my description would be limit as x goes to the left infinitely of f of x. We're saying as we go to the left infinitely, what happens to the height? Well, it's going up infinitely. And then we have to write a separate one, even though they're doing the same thing, gotta write a separate one for this. As x goes to the right infinitely, as we go to the right, what's the limit on f of x? There is no limit. It goes on infinitely in a positive direction, like we see here. In our next example, we have negative 2x to the fifth as the lead coefficient. This is an odd degree with a negative lead coefficient, which means it acts like a line in terms of its end behavior. The limit on f of x as we go to the left infinitely. There is no limit. As I go to the left, it goes up infinitely. The limit on f of x as I go to the right infinitely, or if you want to think about this, as we go to the right, what happens to the output? It goes down infinitely. Take a moment to pause the video and try the next two. So this is positive lead coefficient, odd degree. There's our explanation. It's like a line with a positive slope. The limit on f of x as we go to the left. The limit, make sure that looks like an infinity sign, not an 8. The limit on f of x as we go to the right. Well, as I go to the left, it's going down infinitely. As I go to the right, it's going up infinitely. Same thing you did in Algebra 2, we're just using a different notation. Here, negative lead coefficient, even degree, we treat it like a parabola that opens down. So it doesn't matter, we do have to write both of them out, but it doesn't matter whether we're going to the left or if we're going to the right, because it's like a parabola, they're both going down, both sides. As I go left and right, the graph goes down infinitely. This concludes our clip on the end behavior, describing the end behavior using limit notation.